Hello, good morning everyone. I hope you had a nice weekend. Welcome to the start of our Symposium 370 on winds of stars and exoplanets. And the goal this week is for us to share knowledge between different communities, people working with massive stars, with low mass stars, including our sun, and also with highly irradiated planets to understand what are the similarities and the differences between their outflows. And it's my pleasure today to introduce you our plenary speaker, Professor Stan Wawocki. So Stan did his PhD at University of Colorado on the ionization state of the solar wind. He then went on to Harvard-Smithsonian Center for Astrophysics, where he had a Langley Abbott Fellowship. He moved then to University of California at San Diego as a research scientist, and he got an assistant professor position at University of Delaware in 1987, and he's still in Delaware, and since 1995, he's a full professor. Even though he worked on the solar wind at his PhD, he moved on to work on winds of massive stars. And in addition to research, he also enjoys teaching, and you're going to hear a little bit more about also his new book on Fundamentals of Astrophysics that he published last year. So this is a book aimed at science and engineer majors. And it's with great pleasure I introduce you to Stan. Let's see if he's around.
I'm here.
Hello. So let's give him a warm applause. Thanks, Stan.
Thank you. Thank you very much, Aline. Well, it's certainly an honor to be able to give this plenary talk to open up the IAU 370 session on winds of stars and exoplanets. As Aline mentioned, I mostly have worked on winds from massive stars, although I did my PhD thesis on the solar wind. But one of the great things about this offer was that I got an opportunity over the last month or so to learn about how mass is lost from planets, and I'll try to give a summary, basic physics-based summary. I would really wish I could be there in person to present this talk. I had planned to come in person, but at the IAU 361 in Ireland in May, I basically caught COVID along with 20% of the other people, some 40 plus people at that conference. And it was very difficult to deal with COVID in a foreign country. And I decided I just couldn't risk it, given my age and risk factors, to have it get caught again while I was in Korea. So I told the organizers that I couldn't come, but that I would be happy to give the talk remotely. And that's kind of what we ended up deciding to do. Now, my goal in this talk is to try to emphasize the basic physics of mass loss from stars and planets. I'm not particularly well adept at reviewing the literature, which is very vast in this area, both of winds from stars and exoplanets. So the outline of my talk is that basically I'll spend the first half of the talk on winds, that basically stellar winds of massive stars, to give you some background, since that's a major topic of the symposium. And then I'll move to the thermal pressure-driven winds, coronal winds of the sun and cool stars. And I think this is most relevant for understanding the mass outflows from planets. Planets can also be, their atmospheres can be ablated by the impact of the stellar wind, for instance, as we think occurred for Mars. But you can also have expansion, a hydrodynamic expansion, similar to the solar corona, due to the ultraviolet and X-ray heating of planetary atmospheres. And then in the last third of the talk or so, we'll be focused on magnetospheres of both stars and planets. A particular interesting result recently is that there is this subclass of very massive stars that have strong magnetic fields, and it seems that the radio emission from those stars is very intimately tied to rotation. We think through a centrifugal breakout driven reconnection. And there is similar reconnection that occurs in planetary magnetospheres in the magnetotails. And I'll try to link the two somewhat together, and potentially they have implications for understanding mass loss in magnetospheres of planets. Okay, so the basic outline here, the basic view is that you can think of maybe stellar winds as being in sort of three different categories. The thermally driven coronal winds from the sun and other cool stars that have a very hot corona. And I liken to this to somewhat like a pressure cooker where there's heat coming up from below, the pressure builds up inside the pressure cooker, and there's a release valve on top which allows the outflow. And that's analogous to the stellar wind. The radiation-driven winds from hot stars is a more kind of an outside-in process. That is to say, the radiation driving turns on at some layer near the photosphere of the star without any extra heating, but it's the momentum of the light that actually drives material away, scattered through spectral lines. And I liken this to somewhat like sucking water out of a glass with a straw. The radiation driving is like the suction force. And then all stars tend to get very large as they age, somewhat like people, like myself. As they get very, very large and giant size, their gravity becomes much reduced. The amount of energy you need to escape from the surface of the star is much reduced. And so even convection cells and so forth on the star can lead to spillage over, kind of like Roche flow overflow occurs in binaries. And so I liken this to sort of a glass that's basically overfull and just outflow. Now, I won't be talking too much more about these giant star winds because they're kind of a topic apart. I actually even think that are better thought about in terms of stellar evolution rather than wind theory. And I'll be focusing instead on the two kinds of winds, the coronal winds from cool stars and the radiation-driven winds from hot stars. So let's move on to what kinds of wind mass loss, what kind of mass loss can occur from planetary winds. Well, of course, if a planet like a hot Jupiter gets very close to the sun, it gets heated up by a lot, and then it can lose mass. You still have to overcome the gravity of the planet, and we'll talk about how that occurs. But in some ways, the mass loss, instead of being in sort of spherical outflow, gets into this sort of comet tail kind of structure. And that's going to be very important for understanding one of the differences between mass loss from planets versus stars. And of course, one of the ways we can tell about what kind of atmospheres exoplanets have is when they go in front of the star, they impart signatures on the stellar spectrum during a transit. And by taking the difference between the spectrum while the star is in transit versus out of transit, you can identify even the composition of the planetary atmosphere. For example, this example from the Webb detection of water in the atmosphere of the transiting exoplanet WASP 96b. Now, there'll be more discussion of this at the meeting by these review talks of the people listed here. But the point is that not only can you tell that the planet composition, the atmospheric composition, but you can also tell whether it is asymmetric and outflowing as in a comet tail. And we'll talk about that later in the talk. Now, the key things that we want to know about any kind of mass loss is how much mass is there being lost and what kind of speed does it have. And so in the case of the mass loss rate, the amount of mass per unit time that's lost can be just written as the area of the sphere that the material has to go through times the density times the flow speed, which gives you a mass flux. And for the sun, the amount of mass that the sun is losing is really very, very tiny. It's about 10 to the minus 14 solar masses per year. Since the sun will live about 10 to the 10 years, this means that only about 1/100% of the mass of the sun will be lost during its whole main sequence lifetime. Of course, it will lose more in the red giant phase later. But the typical speed of the outflow of the solar wind is on the order of the escape speed. The escape speed is about 600 kilometers per second. The solar wind varies from about 400 to 700 kilometers per second. And this is comparable to the sound speed in the solar corona, which is very, very hot and has a sound speed of order a few hundred kilometers per second. And that's not an accident. It's actually the gas pressure that's driving the outflow. Now, when you go to hot stars, the mass loss rates can be much, much higher, up to about a factor of 1 billion higher than the solar wind. And this can actually then change the mass of the star over the course of its lifetime, at least in principle. And again, the winds have speeds that typically are the order of a few times the escape speed. maybe 1 to 3,000 kilometers per second for the terminal speeds of the wind. But this is much, much faster than the sound speed in the wind. The sound speed in the winds, these are not coronal winds. These are basically have a temperature that's very similar to the photosphere. And therefore, the sound speed might be at 10 or 20 kilometers per second, and the flow speed thousands of kilometers a second. So they're very highly supersonic. Now, planets can have winds, but they, unlike the solar wind or these winds, they don't necessarily, their wind speeds don't really have to be that fast. For example, in comets, you have outflows that can be quite slow. And we're going to emphasize this point later in the talk. So first, let me review the basic physics of radiation-driven stellar winds. There are review talks about this topic during the course of the symposium as well, and I refer you to those for more details. But again, this is the kind of the suction idea. So here's a basic diagram. You have the gravitational force pulling the gas in, and then you have the radiative flux coming out of the star, and as it gets absorbed or scattered by the opacity of the star, or there's an implied momentum implied. And if you write the flux, energy flux per unit, energy per unit area per unit time and divide by the speed of light, it becomes a momentum flux. And then if you multiply times the opacity, integrate over the frequency, then you get basically an acceleration which can compete with gravity. And the simplest form is basically if you have electron scattering, then you can multiply electron scattering times the flux. You can pull the integral, the opacity out of the integral, then this just becomes the bolometric flux, which is just the luminosity divided by 4 pi r squared. And the point is that the flux drops off like 1 over r squared, but so does the gravity. So that cancels. And the ratio of the radiation force to gravity is constant in space in principle. Just depends on the ratio of the luminosity to the mass. But stars have many different luminosities. If you plug in the value for the sun, this ratio of electron scattering force to gravity is very, very small, only a few times 10 to the minus 5. So radiation forces are totally unimportant in the sun. But as you go to very more luminous stars, since luminosity of stars tends to scale something like the cube of the mass, as you get to very massive stars, then that Eddington parameter. And now, in addition to having the free electron scattering, you can have fluctuated mean opacity. Generally hard to compute the fluctuated mean. That's one of the challenges of doing radiation-driven wind theory. But we'll talk about basically what the key extra opacity is that actually leads to driving a stellar wind. So let's just think of the simplest form of what happens if you have a radiation force that exceeds gravity. Well, in the steady state, you have an acceleration, an advective acceleration, which is given by the net radiation acceleration compared to gravity. Now, there's also a gas pressure force, but in massive hot stars, their winds are very cool compared to the sun, and the gas pressure can be ignored. And then if you just want to integrate this equation, you can just basically use this notation of the ratio of the radiation force to gravity, and then you have sort of an anti-gravity form. And if you just integrate that, you find that the wind speed that you reach will be sort of gamma minus 1, the square of the wind speed, times the escape speed squared. And so, for example, if somehow we magically had a radiation force imparted on all of us, even whether you're in Korea or you're back here in the United States, if the radiation force were twice of gravity, then we would all fly away from the Earth and reach a terminal speed that's of the order of the escape speed of the Earth, about 12 kilometers per second. Now, in addition, this equation that's on the left can be manipulated. If you multiply times 4 pi r squared rho, then that times the velocity, it gives you a mass loss rate. But then on the right-hand side, that 4 pi squared rho gets rid of the 4 pi r squared here in the denominator, and all you have is then the luminosity over the speed of light, the momentum of the light, and times an opacity. Kappa rho dr is a change in optical depth. And then if you do the integral of that, you find that the momentum of the stellar wind is disproportional to the momentum of the light times the optical depth. And then if gamma is very, very large, say, 2 or well, at least 2, this will be of order unity. And so the point here is that O and B stars have momenta that are comparable to the momentum of the light because they're not particularly optically thick. you can actually see down to the photosphere of a OB star. The wind does not block the star. On the other hand, in Wolf-Rayet stars, they can become very optically thick, and you can not actually see the static photosphere in a Wolf-Rayet star. And so photons then multiply scatter, and the amount of momentum in a Wolf-Rayet wind can be actually greater than the momentum of the light. Okay, so that's kind of the basic physics of how radiation driving can drive an outflow. But of course, the key is to find some opacity that can overcome gravity. And a key point about this is that opacity comes from spectral lines, surprisingly. And the reason is that a spectral line is kind of like a resonance for meeting a photon. If you think about it, if you blow out just with your voice, with your mouth, into the air, you make a little bit of sound. But if you blow into a whistle, you make a much louder sound at a very tuned frequency. And the reason is that if that just implies, analogously, for an electron, you go from the continuum into a bound state, the opacity, the cross-section of interacting with light goes up by an enormous factor. And even if you average over the fact that only a few electrons are in bound atoms, the qualities of these resonances is so high that basically averaged over all of the different transitions, you can have a radiation force that can be 1,000 times the electron scattering force, which means you don't have to be near the Eddington limit. You just have to be within 1,000th of the Eddington limit to actually drive an outflow. But the key here is that this is assuming you can illuminate this line with all of the flux from the star. Now, if you go to reality, of course, as soon as you have any kind of number of atoms in a very large cross-section, the line will saturate. And so you would think that would mean that it uses up all the photons and you're done. But no, if you can just get a flow going, then the Doppler effect desaturates the line. And so the line then sweeps through the spectrum and gets a force which continues because of the acceleration of the wind. And so you get a kind of a weird effect that the radiation force on optically thick lines depends on this Q bar divided by a kind of line optical depth given by what's called Sobolev theory. And it scales as 1 over the density. The optical depth scales like the density divided by the velocity gradient that's associated. The gradient will deshadow the line, the density makes it more opaque. And so the key point here is that it's this deshadowing of Doppler effect that allows line driving to be effective. Now, let's go to the way this actually has been applied. There's a classic paper from 1975, Kastrov and Klein, who realized that there wasn't just a single line, there's a whole ensemble of lines with different opacities. And they can be fit pretty well by a power law. And so when you take the cumulative effect of all these lines scattering photons, then you get the optically thin force divided by an optical depth like parameter, but instead of just being linearly proportional to optical depth, it has this power law index alpha, which can be between 1/2 and 2/3, say. And this T parameter is like a characteristic optical depth parameter that depends on density divided by velocity gradient. And of course, then the net result of this, having this line force being greater than gravity, is that you get an outflow, which is comparable to gravity. And knowing that, you can go back and solve for the density or the mass loss rate, which depends on density, and you get an analytic scaling formula for what the mass loss will be like. And it basically scales like the luminosity of the star divided by the speed of light squared, which is just like the mass that's associated with the photons. But then there's this factor, which because Q is 1,000, if gamma becomes of order unity, close to unity, then basically and alpha, say, is 1/2, this can increase the amount of mass compared to the photon mass. And very luminous stars, the photon mass is actually also quite high. And if you plug in numbers, typical parameters like alpha equal to 1/2, Q bar equal to 2,000, luminosity of the star 100,000 times the solar luminosity, you end up getting a mass loss rate which is 1 billion times that of the solar wind. And this mass loss rate can be quite important for the evolution of the star because it's really quite can be quite strong. And so, for example, there's something called the Kanti mechanism, which says that maybe stars that are massive stars, they can actually shed some of their mass during their main sequence lifetime just through their stellar wind. They can shed their hydrogen envelope. And if you plug in kind of parameters that the Q bar of 2000, and then luminosity scales like mass cubed on the main sequence, then you find that you get a scaling formula for what fraction of the mass of the star is lost in the stellar wind over its main sequence lifetime. And the key point I want to make here is that this depends a lot on what you assume about this power law index. If you assume the power law index is relatively small, about a half, then you get that, say 20% of the mass of a 100 solar mass star will be lost on the main sequence. If you then, however, take alpha equal to 2/3, then it turns out it's only a few percent of the mass that's lost. It depends sensitively on this line opacity distribution. So in reality, the people who work on these stellar winds, they spend a lot of time trying to figure out what is the line opacity like and how does it feed back with the hydrodynamics of the stellar wind. And I expect that this issue will be a major focus of Andreas Sanders' review on hot star winds. So that's pretty much what I have to say right now about hot star winds, although we return to them as sources of mass for stellar magnetospheres of massive stars. But right now, the next thing I want to do is talk about thermally driven coronal winds from stars like our sun and cooler stars. And again, this is kind of like a pressure cooker model. And there's some talks during the course of the meeting that will be dealing a lot with coronal type mass loss that we can look forward to. So the basic idea here now is that the key competition is between gravity and not radiation forces, but gas pressure. The gradient of the gas pressure divided by density is an acceleration. And the gas pressure just given by the ideal gas law, density times temperature divided by molecular weight. And you can think of the kT over mu, that has units of speed squared. That's what's called the isothermal sound speed. And so I use the notation here of A equal to isothermal sound speed. And now all you have to do is take the pressure and divide it into the pressure gradient, and that'll give you a scale length over which the pressure changes, because we call this pressure scale height. And if you just plug in the equations there, you find that goes like kT over mu g, which you then can recast in terms of the sound speed over the escape speed squared of the star times the stellar radius. And so the key idea here is that the ratio of the scale height to the stellar radius is given by this ratio of the sound speed squared to the escape speed squared. And depending on what the temperature is and how strong the gravity is, that will determine a lot about how tightly bound gravity holds material in. And for example, for the solar photosphere, about 6,000 Kelvin, the escape speed, the sound speed is on the order of 10 kilometers per second, but the escape speed is 600 kilometers per second. When you square that ratio, it ends up being that it's only about 4 times 10 to the minus 4, the ratio of the scale height to the radius. And that's the reason why the solar photosphere, when you look at it, even though it's a gaseous, something doesn't have a solid surface, it has a very sharp edge to it because the scale height means that the density is changing very, very rapidly. And so you're going from something that is opaque to something that is transparent over a very short scale. Now, if you contrast this with what happens in the solar corona, which is heated up to millions of Kelvin, then the ratio of the scale height to radius is now a number that's a little bit less than unity, about 15% or so. And so you can see that the solar corona emitting X-rays is not sharp. It has a very fuzzy edge to it. And of course, it has also lots of structure because of the magnetic field of the sun retaining gas in some places and allowing it to outflow in others. We'll come back to that later. So now, why is it that the sun has this high temperature corona? This is often quoted as a great mystery, but I don't think it's that much of a mystery. It basically comes back to the fact that if you have a very turbulent atmosphere, there's a lot of mechanical energy propagating up. And as that mechanical energy is damped, the energy has to be gotten rid of, otherwise the gas will heat up. And the way the energy is gotten rid of primarily in the solar atmosphere is through radiation. But radiation requires an electron and an ion to collide with each other. The electron hits the ion, excites it, and that ion then decays and gives off a photon, and that photon escapes and cools the gas. Now, that means that there's this, if you then calibrate, there's this so-called optically thin cooling function, which has the property that it increases with temperature as you go higher and higher and higher, but then it reaches a peak and declines. And the reason is if you get to high enough temperature, many of the ions are getting ionized away, and there aren't very many transitions that can give off photons. And so now if you have energy being deposited in the atmosphere, as the density goes down at higher and higher heights, then what will happen is that eventually you'll get to the point where you can't balance and you get a thermal runaway. In principle, this thermal runaway, if it had just radiation was involved, would have run away to 10 million Kelvin or so. But it turns out thermal conduction plays a big role in bringing energy back into the solar atmosphere, and that keeps the temperature of order a few million Kelvin. So let's just talk more about this thermal expansion of an isothermal corona. Let's assume that the corona is somehow heated and kept hot as it goes up in height. We can think of then a scale length, a temperature at which this scale length h is equal to the to the stellar radius. We can call that an escape temperature. For the sun, it's about 13.8, almost 14 million Kelvin. It never reaches that temperature, but it's a substantial fraction of that temperature. And one of the key points is that if the scale height becomes comparable to the stellar radius, then as you go further and further up, when this ratio between scale height and radius is very, very small in the photosphere, the density drops, the pressure drops exponentially. But if you have a scale height that becomes comparable to the stellar radius, then the base pressure over the terminal, the final pressure, can be a finite constant, and it scales like the ratio exponential to r to the h, or T escape over T. And the key point is that if you then plug in typical temperatures for the solar corona, the number of decades of decline of pressure from the base to the far away from the sun is only about 6 decades for a temperature of 6 million Kelvin. If you have 2 million Kelvin, it becomes only 3 decades. But the ratio of the pressure of the solar transition region, the base of the solar corona, to the interstellar medium pressure, the ratio is 12 decades. So that means that the pressure is much too high. This asymptotic pressure is much too high. And it just can't be that you can have an isothermal hydrostatic corona. Corona must expand. And so instead of having a corona that's just nice hydrostatic, there's outflow. And that's what these streamers are from the helmet streamers. Okay, so now what is the implications of that? If that means that, yes, pressure has to drive an outflow, then we again go back to our equation of motion. Acceleration is minus gravity, but now we have this outward pressure force. But now we have this relationship between pressure and density, that's density times the sound speed. And by the mass continuity equation, density and velocity times the radius squared all have a constant. So you can use that to solve and eliminate the density. And then you get an equation that has the acceleration, the velocity gradient times v. This is the inertial term. And then you have a part of the gas pressure, which then reduces also as an outward force. And on the right-hand side, the part of the gas pressure that's associated with the areal expansion is a positive term. And what you can have is then, if the velocity goes through the sound speed, becomes transonic, the left-hand side goes to 0, the right-hand side also has to go to 0. And that occurs at a radius, which is related to this escape temperature over the actual temperature. That is this is so-called Parker radius, where the flow will become supersonic. And so you can just then plot the topology of all the different possible solutions you could have of that equation in general, the numerator or the denominator. But there's one solution that goes from slow velocity to high velocity, and that's called the solar transonic solution. And that is the only solution that has 0 pressure at infinity that actually maps on to a hydrostatic base. And all the solutions here that are subsonic, they're possible. They're called solar breeze solutions. They all have finite pressure at infinity, so they can't be the actual solar wind. So that's a key argument that the solar wind, for example, what you can do with a modern hydrodynamic code, you just start off with a hydrostatic corona, then pop the bubble at the outer boundary, and then what happens is the gas starts to accelerate near the boundary. There's a rarefaction front, there's a rarefaction front that moves backward until it becomes the solar wind. So you don't have to solve any critical point solutions of the steady state equations. You can just let your time dependent code relax to this solution, which is the only solution which matches the requirement of a slow solution at the base and a supersonic low pressure, zero pressure solution at infinity. So this is kind of the summary that I would give for how the solar wind works. There's basically energy coming up from below by all this turbulence that heats the base of the corona, which is still quasi-hydrostatic, it's subsonic. So a lot of the energy gets lost back in conduction. Some of it also can be lost by radiation. Well, that turns out in practice not to be very important in the open magnetic field regions. But then some energy can actually maybe make it out to even beyond the Parker radius, this where the sonic point is. And in that case, in the inner part of any heat that you put in this inner part will decrease the scale height and then have the density extend higher and higher outward and give you a larger mass loss rate. Whereas any energy you deposit in the supersonic region will just increase the energy per unit mass, that is the flow speed, because it can't change the mass loss rate. It's already fixed at the sonic point. So this means that we now, if you want to really understand how much mass loss is from a solar corona, you need to basically take into account the energy. You have to know what the energy balance is. That isothermal equation was a nice toy, but it isn't the actual thing that determines the mass loss because the density scales out of that equation. And so what you have is the kinetic energy, the potential energy, then there's the internal energy of the gas called the enthalpy. Then there's the energy that's being added by some kind of either magnetic reconnection and then the loss due to conduction. So in practice, what happens is that this enthalpy term is not particularly important. It's dominated by these other terms. And therefore, if you really want to know how much mass is being lost, you just have to do an energy budget. Mass loss, the kinetic energy plus the potential energy of the wind has to be balanced by how much heat you put in minus how much you lost for cooling or to conduction. And so that's kind of the name of the game if you want to quantitatively model how the solar wind loses mass. It's basically an energy balance. And it works out that if you put the amount of energy that's being put in by mechanical energy, by waves and magnetic reconnection, then you get a mass loss rate that's about 10 to the minus 14 solar masses per year, and a flow speed that's anywhere from 400 to 700 kilometers per second on the order of the wind escape speed. Okay, now what I want to do is I want to try to put this number in context, this 10 to the minus 14 solar masses, in terms of how much mass loss, for example, is lost by just the fact that the sun has photons, and photons there's mass energy associated, anything that has energy has mass. And so you take the luminosity of the sun divided by c squared, that's kind of an energy loss. And it turns out that the mass loss rate of the solar wind is only about 15 to 20% of the mass loss of the photons. It's really very puny, about 10 to the 12 grams per cubic centimeter, grams per second. Well, now let's ask ourselves, well, how does this compare to the radiation loss of the solar corona? We have this picture. This is an X-ray picture of the solar corona. And that's very homogeneous, right? Because the places where the solar wind is able to escape, the open magnetic field regions, are called coronal holes. They have very low density, and you can see they're very dark. You don't really have to worry about radiative losses from those regions. Almost all of the energy that gets deposited to the corona comes out as solar wind, just like our pressure cooker model. But here, you kind of have the lid of the pressure cooker without any rocker arm, and it just holds the gas in until it gets so hot that it radiates it away. And that comes out as ultraviolet and X-rays. And so now if we ask ourselves, well, how much of the solar corona energy that's put into the solar corona comes out as X-ray and ultraviolet light versus the kinetic energy? Well, it turns out they're pretty comparable. As you can kind of see from this picture, you can't see the energy being lost in the coronal holes, but it's there. It's coming out as solar wind. And here, where it's being held down by magnetic fields, it's coming out as photons. Okay, so now where do we stand in terms of, all right, so this is so the point is that the solar wind is very puny in terms of amount of mass loss. So, but it turns out it's not negligible in terms of how much angular momentum can be transported, because the magnetic field of the sun can extend the influence to very far away, so that the amount of angular momentum that you lost, which is given by this scaling law that was first derived by Weber and Davis in the 1960s, mass loss rate times the rotation frequency times the Alfvén radius. And the Alfvén radius is how far the magnetic field can sort of force the wind to carry away angular momentum. And that turns out to be about 20 times the solar radius. And the upshot of this is that the time it takes for the solar wind to spin down is comparable to its main sequence lifetime. And this is possibly one explanation for why the sun is such a slow rotator. But if you go to other stars, you find out that they're stars with different ages and different conditions. It turns out that you can fit the rotation period of cool stars with what's called the Szymanowicz law. It scales as the square root of the age. And this can actually be derived from this Webb and Davis theory if you just assume that the magnetic field is proportional to the rotation frequency, or 1 over the period. And the time scale is about 7 billion years times for a magnetic field, an initial magnetic field of only a couple of Gauss, divided by -2. And so if we now plug in suppose the solar corona had a initial rotation of only 1 day instead of 27, well, then it turns out that if you work it out, the spin down time would have to have been quite short, only a few million years, about 6 million years. And the magnetic field would have to have been about 27 times bigger than it is today, about 67 Gauss. And this leads to the whole study of what's called gyrochronology. With all the data we have from Kepler and TESS, you can actually track the spin down of massive stars. And the implication, low mass stars, cool stars. And the implication is that the young sun was likely much more active, had much more activity, like coronal mass ejections. And then these coronal mass ejections impacted the planets like the Earth. But most importantly, you have planets that don't have a magnetic field. Then what happens is that any solar wind or mass ejection that comes from the sun can then directly strip the atmosphere of the planet. And this is thought to have occurred in Mars. Mars has a much less, lots of evidence that Mars had a much thicker atmosphere in the early part of the solar system, maybe the first 100 million years, but that today it's only about 1% of the surface pressure of the sun, such that you can't have, for instance, liquid water on the surface of Mars. And again, this probably had a lot to do with the solar wind stripping. And when we look at comparison, of course, with Mars, the Earth, however, is unfortunately shielded somewhat by the fact that we have a strong dipole field generated by our iron core, and that prevents the direct impact of the solar wind on the atmosphere. And so Earth does not really lose much mass due to solar wind directly impacting. However, just as it happens in comets, the heating of the atmosphere can cause an expansion. Now, in comets, there's almost no gravity. So once you melt the ice and turn it into a gas, a vapor, then it's almost inevitably going to escape. But you can see how the solar radiation drives material away from the dust that's in a comet into what's called the dust tail, which is very slow outflow, versus anything that gets ionized then gets entrained in the solar wind and almost moves out at a very high speed of the solar wind. The orbital speed of the comet is typically tens of kilometers per second. And so you get these two tails. And this is kind of a sort of cautionary tale for what happens in planets. Basically, a planet will also have its atmospheric outflow be stripped away from the sun, from the star. So now but the difference is that planets have strong gravity, and so you have to heat the gas up to pretty high temperature. And so now if we go back to this concept of escape temperature, you can see that the escape temperature of a body scales like mass over radius. You normalize that to the 13 million Kelvin of the sun, you can recast it in terms of the density ratio times the radius. And since planets are much smaller than the sun, then this lowers the temperature by a lot, but still for Jupiter, which is about 1/10 the radius and has very similar density, about 1.4 grams per cubic centimeter, that's the solar density, the Jupiter will basically get to be about 100 it needs a temperature, escape temperature of about on the order of 10 to the 5 Kelvin. The Earth, being another factor of 10 smaller, although it is a little bit denser, ends up being about 4,000 Kelvin. And the key point is that even though you might have a planet that goes very close to a star, the equilibrium black body temperature never reaches these kinds of numbers. For stars that are maybe half the temperature of the sun, they only reach a couple of thousand Kelvin, even if the orbit is right at the surface of the star, the distance of the orbit. And so the bottom line here is that just black body heating is not enough to drive escape from a planet. Instead, you have to utilize the fact that the corona of these stars are giving off solar, as just as the sun is giving off ultraviolet and X-rays. And this ultraviolet and X-rays can then heat gas to temperatures that can be hot enough to escape. And the key idea here is that X-ray ultraviolet photoionization is a much better, is a much stronger source for heating, more direct than black body radiation. So if we now want to quantify how much masses can be lost by this X-ray ultraviolet heating, again, it's a matter of just counting on how much energy you can deposit to give the material an escape energy. And then there's some kind of efficiency to ultraviolet heating times the cross-section of the planet. And you can then solve for the mass loss rate given the luminosity and X-rays and so forth. And for the sun, as we talked about, the X-ray luminosity, the XUV luminosity is about 10 to the minus 7. And then if you plug in numbers, well, the atmosphere of the Earth, for example, is only about 1/1,000,000th of the mass of the planet Earth. And then if you then work out what the lifetime of the atmosphere of a hydrogen to exist at the current rate of ultraviolet heating from the sun, it's about 2/3 of a billion years. But of course, if the sun was much more active in its early years, it would have ablated any hydrogen much sooner. And this is one of the reasons why planets like the Earth don't have any hydrogen in their atmosphere, except for what's locked up in water. If you take Jupiter, which is made up of hydrogen, but doesn't really have an atmosphere, the whole planet is gas. You plug it in at a distance of 2 solar radii, so a hot Jupiter, you find out that the mass is about 10 to the 10 grams per second, about 1% of the solar wind mass loss. And it would take over 4 trillion years for Jupiter to be evaporated. And that's why, exoplanets are really, hot Jupiters are really not affected. So a key point here is that thermal escape can deplete the atmospheres of low mass rocky planets, but not high mass gas giants, even hot Jupiters. And now just to ask, well, how do we know that there are these outflows? Again, you can just use transit light curves. This is data transit as a flux as a function of a transit of the exoplanet in front of the star. And what you can see is that you can fit these data with different models. Here's a model with 10 to the 10 grams per second, but with 20 times the solar ultraviolet flux. And then that matches the light curve very well. So this star probably has more ultraviolet and then drives mass loss from this hot Jupiter around this star. But you can also get information about the outflow speed by looking at the Lyman alpha spectral line. Here's a plot of the spectral line at various times out of transit, before transit, post-transit, and in transit. And the key thing here is that both the in-transit and post-transit have very strong absorption on the blue edge. You can't really get any information here because this is all interstellar medium absorption. But the wings of the line are strongly affected by the fact that there's an atmosphere ablating off of this hot Jupiter. And what's interesting is that the speed goes out to more than 100 kilometers per second, which is much greater, about factor of 5 greater than the escape speed from a hot Jupiter. And so the bottom line is that as a consequence, we think that this flow is either entrainment in this outflowing stellar wind or driving by Lyman alpha. Okay, so now that's pretty much the first part of the first 2/3 of my talk. The last third I'm going to spend on talking about planetary versus stellar magnetospheres. And they have some similarities, but one of the key differences is that the stress on the magnetic field for a stellar magnetosphere is from the inside outflowing stellar wind. It comes from the inside material that's trying to flow outward, whereas planetary magnetic fields are stressed from the outside by the impacting stellar wind. And so let's try to look at how this occurs. For the sun, there's a classic paper from the 1970s by Newman and Kopp that basically says, let's start with a dipole and then just put in a hot corona and then let it expand. Well, this is done with a very clever iterative scheme, because back then you didn't have very sophisticated MHD codes. And the bottom line was that the expansion then strips the material open and forms these field lines that are moving out radially. And in this case, the field line here is of opposite polarity from the field line here. Therefore, there has to be a current sheet in between. Modern day, for instance, my colleague Asif Abdullah, as a first test problem when he was working on his thesis, basically just turned on the hydro MHD code, and it goes to this basically Newman and Kopp type of structure. And this basically explained the so-called helmet stream structure of the solar white light corona. Here's where the magnetic field holds the gas back, but eventually the wind overwhelms the field and drives it out. And it's called a helmet streamer because it kind of resembles a German World War I army helmet with a pointed thing at the top. And now let's talk about the different kinds of stars. The solar mass stars have a convective envelope that generates the magnetic field by the interaction with rotation, and it leads to these very complex magnetic activity cycles, like the 11-year solar cycle. But now, if you look at high mass stars, their hydrogen never recombines because they're hotter, and as a consequence, they don't have strong hydrogen recombination convection zones. The radiative transport is pretty close to being radiative all the way to the surface, except for a narrow layer that's due to iron. But we'll talk about that perhaps in the discussion. But the point is that they have no dynamo. Yet spectral polarimetry has found that about maybe 8 to 10% of high mass stars, so O and B type stars, have fossil fields that can range anywhere from 100 to 10,000 Gauss. And this is probably from some earlier epoch with a star. And if you have that kind of strong field and a radially driven wind, we want to figure out what will be the consequence for the outflow competing with this magnetic field. So there's a consortium of researchers that work on this. That's called the Magnetism of Massive Stars Consortium. It's led by Greg Wade, and I, along with 50 other colleagues around the world, have spent many years collaborating with people to study these magnetic massive stars. And the key thing, a key parameter that one wants to consider is what is the ratio of the magnetic energy density to the kinetic energy density of the wind outflow. And the place where that parameter becomes a order unity defines what we would call the Alfvén radius, where the magnetic field gets ripped open. But because the magnetic field is dropping as r to the -3, which then means the square drops as r to the -6, whereas the density of the wind only drops as r to the -2. Well, 6 minus 2 is 4. The 1/4 root of this sort of base parameter, this dimensionless parameter, called the magnetic confinement parameter, will determine essentially where the Alfvén radius is. And so this is a case where there's an Alfvén radius of 100. I'm sorry, a star of 100. So the Alfvén radius turns out to be about the square root of 10, or a little over 3 stellar radii. Anywhere below where the magnetic field is basically dominant, the wind, instead of having a hydrostatic material here, the gas is very, very low temperature. It's only on the order of maybe the temperature of the star, or maybe 20, 30, 40,000 Kelvin. Basically the gas from each foot point flows upward, compresses and shocks, and then cools, then falls back down on a dynamical timescale. So we call this a dynamical magnetosphere. That's in the case where you don't have any rotation. What if you put in rotation into the mix? Well, this closed magnetic loop regions will co-rotate rigidly with the star, and if then define a parameter of the rotation speed at the equator compared to the orbital speed at the surface, if you keep co-rotation, then there'll be some radius called the Kepler co-rotation radius, where basically the outward centrifugal force will be balanced gravity. And that means since the centrifugal force above the Kepler radius is greater than gravity, material can't fall inward. And so what you do is instead you accumulate material in this region between the Kepler radius and the Alfvén radius until the material builds up to the point where it's so strong that it overwhelms the tension, the magnetic tension that's holding it down, and you get these outbursts, which we call centrifugal breakout events. Now that occurs in ideal MHD, but we have to ask ourselves whether that's appropriate to real plasmas. Okay, so that's the key thing, is that there's two kind of magnetospheres, the dynamical magnetospheres from slow rotating stars and centrifugal magnetospheres. And now we can do a series of models with increasing rotation. And this is now plotting quantity, which is the mass distribution in radius, delta M over delta R, as a function of radius and time for various values of the rotation parameter and the magnetic confinement parameter. And as you go to stronger and stronger field with no rotation, you just get a bigger and bigger Alfvén radius, and material just falls from a larger and larger height. But if you now go to a moderately rapid rotation of half the critical rotation, and then you increase the magnetic field, well, now material gets trapped at this region around the Kepler radius, and you build up what we call a centrifugal magnetosphere. So that's kind of an interesting distinction. You can actually build up a lot of material in these magnetospheres from rapidly rotating stars. So this suggests a way to classify the observations. There are some, at the time that this paper was written in 2014, magnetic fields basically were discovered in sort of 60-something O and B type stars. I think now we're approaching closer to 100. But the point is that you can classify any detections of magnetic fields using spectral polarimetry in terms of how rapidly rotating they are versus their magnetic confinement. Strong confinement to the right, rapid rotation going up. And this line here divides the place where the Alfvén radius and the Kepler radius. Everything in the upper right has a centrifugal magnetosphere. Everything in the lower left has a dynamical magnetosphere. And what's interesting is that all of the O-type stars here lie below this line, meaning they're slow rotators, except for this star, which is a binary Plaskett star. And that's probably spun up by body interaction. And the point is that these stars have really lost their angular momentum due to the wind, the very strong magnetized wind. Those stars have very strong mass loss rates, and therefore they can be spun down very quickly if they have a strong magnetic field. And so this brings to the issue of spin down of magnetic OB stars. Again, we use this Weber and Davis formula, but now the Alfvén radius squared is proportional to the square root of this confinement parameter. If you plug in the numbers, you find that the spin down time of these magnetic massive stars is much less than the main sequence lifetime. Only these now do not spin down as a power law the way the schematic is, because there's no feedback between the mass loss and rotation of the star. Instead, they just spin down sort of exponentially. That is, the period just increases with age compared to the spin down time. So if we now pick out stars that are up here that haven't been spun down yet because they're either very young, but they're also because they're B stars and don't have a strong mass loss rate, so they can live for a little bit longer before they're spun down. So a star like this, Sigma Orionis E, has a very strong centrifugal magnetosphere, and we can model its H alpha, its characteristic observations. For example, the H alpha emission from such a magnetosphere. This case, the magnetic field is about 10,000 Gauss. The magnetic confinement parameter is about 10 to the 6th. The rotation is about half critical. And what this means is that it has a very powerful centrifugal magnetosphere. And then you can actually model this and then compare to observations. What happens is that these magnetic clouds, which end up imparting signatures to the photometric light curve, which look a lot like a transiting planet, but they're not. They're magnetic clouds that go in front of the star. They also impart H alpha emission and a variable spectral line in H alpha. And at the same time, you can follow the spectral polarimetry, the magnetic field variation with rotation. So what this can lead to is developing what's called a dynamical spectrum of the H alpha variation as a function of rotational phase, plotted versus the Doppler shifted velocity from line center. And what you find is that you get this very complex S-wave pattern that's predicted by the model. And this is what you see when you observe H alpha from this star. And the overlap in the is really quite striking. It really tells you that there really is a centrifugally supported magnetosphere that's strong enough to emit an H alpha. But now the question is what determines what the density of this centrifugal magnetosphere is? Is it just that it builds up to the point where the magnetic field is overwhelmed by the gas, centrifugally being driven outward, centrifugal breakout? Or is there some sort of unideal leakage of material as it diffuses outward? Well, in the recent work by Matt Schultz, we examined under what conditions these stars, these magnetic massive stars, have H alpha emission. And it turns out that first of all, the onset of H alpha emission doesn't seem to care about the luminosity of the star. And if this depended on the wind feeding rate, as you would expect for a leakage type model, you would expect there to be a trend here, and yet there is no trend. And then moreover, when you plot the magnetic field at the Kepler radius compared to the magnetic field at the Kepler radius that would make, by the centrifugal breakout model, the H alpha be optically thick, then you find that there's a very nice correspondence to when you actually start seeing H alpha and when the breakout theory suggests that there should be there. So centrifugal breakout seems to be the controlling mechanism for mass loss for magnetospheres of these stars. And so again, I like to think about this simple analogy: no matter how fast you pour water in the water in the glass is by the size of the glass. If there was leakage, it would depend on how rapidly you put in the water versus coming out. And so this seems to be ruled out. It must be breakout. Now, here is a really interesting fact that the radio emission from these magnetic stars, these are also observed often to be non-thermal radio emitters. They show a kind of circular polarized radio emission that are thought to arise from electrons that are gyrating around the magnetic field. And that also is independent of the luminosity, plotted here in the opposite direction, and depends on the ratio of the alpha radius to the Kepler radius, which only means that only stars that emit radio are rapid rotators. And so again, this seems to be related to the centrifugal breakout model, only now the key issue is that centrifugal breakout implies that there is magnetic reconnection, and that magnetic reconnection can basically be a mechanism for accelerating electrons and then making them give rise to radio. And so here are the competition between an earlier model by Trillo, who said that, well, these electrons are accelerated in the current sheet of a stellar wind without any mention of rotation. But since we now seem to think that rotation is key, my colleagues and I have developed this idea of centrifugal breakout as being the key to accelerating electrons and giving rise to radio emission. And the theory of centrifugal breakout, as I've developed in a paper I recently wrote, predicts that it should scale as the rotation frequency times the volume of the magnetosphere times the magnetic field strength squared. Now, magnetic field strength squared is like an energy density, multiplying times the volume is a total energy in the magnetic field, and then rotation frequency is a rate at which that's being dissipated. So this scaling would imply that something like the energy of the magnetic field is being dissipated every rotation period or so. And now that doesn't necessarily have to be the case, but that's the predicted proportionality. And then when you compare that to the radio emission, it turns out that the radio emission is directly proportional to this centrifugal breakout luminosity, with about a reduction factor of about 10 to the 8th. That is, only 10 to the 8th of the energy actually ends up in emitting radio. The other goes into other loss mechanisms. But the fact that they're so strongly proportional suggests strongly that centrifugal breakout is the key mechanism for radio emission from these magnetospheres. Now, what's the relationship to planets? Well, planets also have these kinds of reconnection events. For instance, the Earth has the solar wind impacting it, but the solar wind has these coronal mass ejections and so forth, and they can then cause ejections of plasma from the built-up plasma in the magnetotail reconnection. And the magnetic tail real connection is associated with things like substorms and enhanced aurora. So that's evidence that indeed this kind of same process occurs in planets like our Earth. But in the case of Jupiter, for example, we have two sources of stress. We have the solar wind impacting the magnetosphere, but also Jupiter has this volcanic moon called Io. And when sulfur atoms are kicked up by the volcanoes of Io, they get ionized by the solar UV light, and then they get trapped on the magnetic field of the rotating Jupiter. And then they want to flow outward by the same basic centrifugal mechanism that we have in massive stars. And they then force a reconnection of the magnetic field. And indeed, the radio that's observed from Jupiter, some in certain classes of radio from Jupiter, I think it's the decameter radio emission, seems to be linked to the position of where Io is. And so we have this final comparison, very speculative idea that if we take the scaling law that we derive for early type stars, magnetic early type stars, extrapolate that downward, then there's another class of stars that are radio emitters that are much cooler, the ultra-cool dwarfs, cooler than about M7. They're also thought to have magnetic fields and be rapid rotators. So we think they're analogs, cool star, very cool analogs of the hot star magnetospheres. But then if you extrapolate that down many, many decades, you also find that Jupiter falls on this scaling law. And so that does have some suggestion that maybe there's some link to the radio emission from Jupiter and presumably from also other exoplanets. All right, so this is kind of the summary. Let's see, where do we stand here? This is about an hour now. I am going to put this up, but I'm not going to go through this in detail because I want to do one more thing. I want to basically, I'll come back to this slide and then we can use that as part of our discussion. But I also wanted to introduce some key themes and issues that maybe might be important for the discussion either now, but also during the course of the conference. The first is that this idea that thermal expansion is a key to understanding both the cool star winds like our sun and potentially planetary mass loss. But there's also this other idea that the wind from the star can impact the planetary atmosphere and ablate it if it's not protected by a magnetic shield. One of the key differences between the two processes is that the energy that's propelling this thermal expansion from the sun and other stars is coming from inside, whereas from planets it's coming from the outside, whether it's from heating from the ultraviolet light or stressing from the impact of the solar wind. And this means that then stellar corona and outflow are going to fill 4 pi star radians. They're going to go out, flow outward, whereas the mass loss from a planet will get turned into this comet type tail. And that means that they don't have to satisfy these conditions of pressure being small infinity, which means that they can be subsonic. They can be subsonic and you can still lose a lot of mass. You don't need to drive the mass away in a supersonic way the way you do in the solar corona. You can just drive it away because you have a very extended atmosphere because the scale height becomes very large. And then there's the question of, well, is it a hydrodynamic expansion or what is the role of the magnetic field? But also many people have said, well, you shouldn't be thinking about this as a hydrodynamic process at all. It should be like an exosphere where the individual ions just escape because they get to be such high speed. Now, there was a similar debate when Parker introduced the concept of a hydrodynamic expansion called the solar wind between Chapman and Chamberlain and so forth. And generally speaking, because the conservation equations are really just moments of the Boltzmann equation, you really aren't that limited in how you treat it as a hydrodynamic expansion. One difference is that hydrodynamic expansions, a single fluid will drag heavier ions with, say, hydrogen. So that can be a factor. But generally speaking, I think this is an interesting issue about how important it is to include sort of non-classical hydrodynamic concepts. And again, it comes down to this idea that right now I've been talking about the escape of hydrogen, but of course, the abundant elements of atmospheres of rocky planets are things like carbon, nitrogen, and oxygen in various molecular configurations with hydrogen. And those atoms are harder to make escape because they're heavier, and the escape temperature is accordingly higher. Then you have this issue of Mars versus Earth versus Venus. Mars has got its atmosphere been depleted by the solar wind ablating it. Earth has been protected from that by this magnetic field, but Venus doesn't have much of a magnetic field. It's a very slow rotator. It doesn't seem to have a strong magnetic dynamo, and yet the atmosphere of Venus is 100 times the surface pressure on Venus is 100 times the Earth's. And that's because as you get closer, you also have more outgassing and volatile elements that escape the rocky planet. And so the process of whether an atmosphere will be ablated or not is not so simple. It depends also on the internal physics of planet formation. Then we have the issue of hot Jupiters versus super Earth. We're probably more interested in Earth-type planets and what happens when they start getting close to a star, if it's a cool star. And that leads to this issue of, well, what about coronal activity and how is that affected with age or spectral type of the star, the host star? And that means that you not only have to include the equilibrium temperature to decide whether a planet is habitable, but you also have to consider the activity of the star, the so-called living with the star paradigm, and what role does the activity of the star play in the planet? Okay, so as I finish this talk, I do want to sort of note that my approach here is kind of my typical approach of trying to explain physics in sort of intuitive and using some math, because I don't think you can really understand physics without using some equations. And so this comes a lot out of a long experience of teaching, which Aline alluded to at the beginning, that I find that by teaching, you really have to reduce explanations of physics to its basics. And I've been teaching a course for over a dozen years called Fundamentals of Astrophysics at the University of Delaware. It's aimed at, it's a one-semester course aimed at science and engineering majors, which basically assume that they already know some calculus-based freshman physics. But then I try to then build on that and go all the way from basic properties of stars to cosmology in 5 sections, and I try to cover this in one semester course. And I've been doing this for so long, eventually I got approached by Cambridge University Press, and we were able to turn my notes for this class into a textbook. And I was able to keep the price relatively low for the paperback version. And so I hope you'll maybe take a look at this if you are teaching astrophysics in your own universities. All right, with that plug underway, I'm going to just put back my summary slide that I just flashed up earlier. And hopefully this will be a basis by which we can have some questions and leading into some discussion for the conference, the symposiums to start tomorrow. Thank you very much for your attention. I really enjoyed all the physics that went into, that I've learned from going into presenting this talk. Thank you.
Thank you very much, Stan. Great. Do we have questions?
Hi, thank you very much for the great talk. I'm Raíssa Estrela, I'm from NASA JPL. And my question is, does the solar wind play a major role in the loss of water in Venus?
I have to say that I'm not an expert on loss of water. I think there is some discussion about that water will get split by the UV light and then escape. But I've tried to do some background reading about why Venus is so dry. And I really am not an expert on this, but I think that it potentially plays a role. That is to say, Venus will lose its hydrogen because of the ultraviolet heating. And of course, hydrogen is key to having water. But why water itself would be so depleted in Venus is still, I think, more complicated than I'm able to answer. But that's a very good question.
Mm-hmm. Thank you. And my second question is, and apologies if you mentioned during your talk and I missed it, could you scale this equation for the solar wind that's based on the Parker wind with this community law in order to calculate the mass loss of the sun due to solar wind for the young sun?
Yeah, basically, I think, I mean, this is a very simplistic, simple model, but I was quite amazed. You know, I was a graduate student in the University of Colorado, and I actually knew Andy Skamanich when I was a graduate student. He was already a scientist, a tenured scientist at High Intel Observatory, part of NCAR. And amazingly enough, he's publishing papers in 2019. He has a really nice paper on the Skamanich law and what it implies. And through that, reading that paper, that I ended up realizing that you could actually explain his law with just using a simple Weber and Davis type of scaling analysis. That actually comes, I'm not the first person to realize that. That comes from many people that he cites in this paper. But what I was really quite impressed by is the fact that this scaling in the sort of split monopole form of the Weber and Davis analysis, it turns out that the mass loss rate scales out of the spin down time. And so you get this remarkable thing that you can derive, which is that the spin down time is only related to properties of the sun, like its radius and density, times something about the solar wind. How fast is the solar wind? About a few hundred kilometers a second. And then this is the amount of magnetic flux that it's actually able to escape into the interplanetary medium. And that's the sort of the idea of the Weber and Davis model, is that you get material that's ripped open into this flux. And so the point being is that when you go through this analysis, if you assume that the early sun was very had a much faster rotation period, then it presumably had a very stronger rotation convection dynamo, which then makes it have a stronger magnetic field. And to the extent that the coronal heating is related to the magnetic dissipation and magnetic waves and so forth burning up, you should indeed expect there to be a much stronger solar wind in this scenario. However, within the Weber and Davis formalism, that stronger solar wind doesn't basically change the scaling, because, well, we have to go back to this Weber and Davis formula. In the monopole form, the mass loss rate here is proportional to the angular momentum loss, but the alpha radius has an inverse dependence on mass loss, and that cancels in the monopole, the split monopole Weber and Davis formalism. So the bottom line is that, yeah, you would expect the solar wind, the sun, to be much more active when it was much more rapidly rotating, but also to have a stronger solar wind. And of course, that has all kinds of implications for the early evolution of planets in our solar system, including the stripping of Mars's atmosphere.
Thank you very much.
I think, Aissa, we're going to have some talks today in Division E, but maybe they're taking place simultaneously with yours. But we'll have more discussion on rotation during the week. I have one question. Please, if anyone have a question, come to the microphone. I can't wait for my question.
Hi Stan, Uxana, Belgium. Great talk, full of physics as usual. My question is a remark that you made at the beginning that intrigued me. Of course, you didn't talk much about the wind of red supergiant, and this is fine because there's not enough time to do everything. But you mentioned that the red supergiant's winds are better tackled from a stellar evolution point of view, and I wanted to hear more about what you are thinking behind that remark.
Yeah, well, thank you for that question. This comes back to, you probably know Dylan Key, who was a postdoc in Belgium in your institute, has done some very nice work on turbulent effects of turbulence on extending the scale extension of giant stars and allowing them to have mass loss. And of course, these big 3D MHD simulations I believe at the talk I gave for the IAU 365 last fall, we did talk about this a bit more than I was able to do today. But the basic conclusion that I have is that we spend a lot of time asking ourselves when we talk about these cool stars. Let me go back to that diagram. We spend a lot of time sort of asking how many angels can dance on the head of a pin kind of thing, right? I mean, the gravity, if you take the sun and you expand it by a factor of 100, which is what happens in the red giant phase of the sun, then the gravity, the gravity goes down by 100 squared, and the scale height, basically what it's saying is that even at temperatures, photospheric type temperatures, the ratio of the scale height to the radius is now no longer tiny. And that means that convection cells that occur can extend well above the star, and then a little bit that can leak out. And we can spend a lot of time asking ourselves, how does this lead to net mass loss? But I like to think about it as sort of the wrong way to think about it, because imagine that you have a fountain which is being fed from below, and then there's an edge to the fountain where the water flows over the edge. You could spend a whole lifetime calculating the pressure gradient from the center of the fountain to the edge, which drives the water over the edge of the fountain. But the ultimate reason that the fountain is losing mass is that the water is being pumped up from below. And so I think a better way to think of super winds from very giant stars, and this means not just red supergiants, but asymptotic giant brown stars, all the stars that get very, very large. I think the way to think about it is they're just really kind of reaching their Roche lobes, as it were, as they would in a binary system. They would spill matter over onto the other star. The only thing is that little pulsations can now kick material away from the star. So it's a lot more, to me, like the overflow of a glass or overflow of a fountain. And I kind of mentioned this at the IAU 361 to Dylan, and he and I have, talked about maybe pursuing this. I think I even mentioned to a few other people there that I think this is maybe a better way to think about mass loss from giant stars, rather than trying to calculate their hydrodynamic outflow, to just think about the fact that the evolution is forcing them to get bigger and bigger and bigger, and then their outer atmospheres are just becoming kind of unbound. And you can imagine doing some numerical experiments with, say, MESA, where you just take the mass and lift it off the edge and ask what is the net result of that for the stellar evolution. So yeah, I do kind of believe, even though I'm a wind person and would normally advocate for having to study wind physics, I actually think that's kind of the wrong approach to understanding mass loss from giant stars.
All right, thank you for this explanation. I do understand now better what you meant. And maybe for the audience, I just want to re-emphasize that the mass loss, the amount of mass which is lost from the red supergiant phase, is an important missing element in the evolution of massive stars.
Yes, indeed it is. And who I think that it would be a really good idea for us to have some further discussions, with the other people in Belgium and including Dylan. I think this is an interesting area to pursue, I think. It may help us understand a lot of things. I mean, like, the way stars end up as, a planetary nebula and stuff like that. I think that, and actually, to tell you the truth, this is also discussed a bit in my book.
Okay. All right. Thank you so much.
We have another question in the audience.
Thank you for that wonderful talk. I really appreciated the learning about the mass loss from stars and planets. I was wondering if you could spend a minute just sharing your thoughts about mass loss from accretion disks. The regimes are so different. You can have hot disks and cold disks, and there's irradiation, winds impinging on the disks, and there are magnetic fields and those sorts of things. So I learned a great deal of intuition from your talk, so I was wondering if I could learn a little bit more from accretion disks.
Yeah, well, of course, I haven't really actually published too much on accretion disks. I did do some work on them in the early 2000 era, but I've certainly followed the literature, the basic literature. And of course, quite analogously, there are accretion disks. Well, let's put it this way. Accretion disks can be driven thermally from, accretion disks of protoplanetary systems. They get hot and then they expand and they have thermal expansion. One of the things I want to say is that thermal expansion is really kind of a limited mechanism, because if the density gets too high, then most of the energy will be lost in radiation. So the corona is not an accident that the solar corona has very, very limited mass loss. It's very hard to you can never get a billion times the solar mass loss rate with thermal expansion, because it'll just be so dense, it'll just radiate all the energy away. And so there's a limit to how much you can drive from thermal expansion. So I mentioned Dylan Key. He was my graduate student, and his thesis was on ablation of disks by radiation forces like massive stars coming close to the accretion. Then they get hit by radiation, and the material actually gets ablated. And I think this is, for example, there's evidence for this occurring in BE star disks, which are kind of ejected from the rapid rotation. And then what happens is you don't see very many OE stars, because the radiation can ablate those disks very quickly, whereas you do see lots of BE stars where basically the ablation time is longer. So that is one factor. And as you mentioned, magnetic fields play a big role in accretion disks and the physics of accretion disks. You can get these hoop stress formulas, and you get jets and all kinds of stuff. But generally speaking, I think the physics is very similar. The difference, of course, is that instead of that at the center of the disk, the gravity goes away, and it's only the deviation away from the disk. The gravity sort of increases as you move up from the disk center, and so that leads to some very interesting differences. But for example, disks from quasars and so forth, where you have a very strong radiation field, you can get this. I think there's work by Murray and Chang, which they talk about, material being driven off the surface of the disk, and Daniel Proga has also done lots of really nice work in this area. But I think the physics there's a lot of overlap in the physics, but because of the geometry difference and the difference in how gravity works, there are some important differences. And I think maybe it's analogous to what I was trying to cover here. There are similarities, the way there are similarities between coronal expansion and planetary expansion. There are similarities between disks, all the different kinds of disks. You can have thermally driven disks, you can have radiation-driven disks, disk winds. But I think that there are also important differences due to the geometry difference and the difference in gravity. But it's an area that I'm also very interested in. I just haven't had time to publish very much in that.
Thank you.
I would like to ask one question about observations. You mentioned the alpha factor, and you said that it makes a real big difference for massive stars, whether alpha is half or 2/3. I mean, the amount of mass they will lose during their lifetimes. How can you observationally constrain values of alpha, for example?
Well, it's really a parameter that is set by the ionization and excitation physics of the wind. And so there's really nice work that was recently done by Luka Poniatowski at Leuven. He's now going to work with Andreas Sander, where he basically calculated the line distribution for different assumptions about temperature and density. And this allows you then to basically put this into dynamical models in a sort of self-consistent way. But then there's some people, like for instance, Andreas himself, who works a lot on whether you can really treat this as an LTE type of process, or whether non-local thermodynamic equilibrium can be important. But you don't have the access to the actual spectrum, because all these lines are in the ultraviolet. And so it's unlike, so you don't really have direct observational access to the actual line distribution, because the parts of the spectrum that are hard to see, especially when you go to very hot stars where a lot of them are in the far ultraviolet. So I think what you do is you try to match predictions of mass loss rates with what you infer. And a key wrinkle, and I didn't talk about this because I couldn't talk about everything, but a key wrinkle in that is that most of the diagnostics of mass loss depend on something like, say, H-alpha recombination, which is a density squared process. Radio emission is also another form of diagnosing mass loss from massive stars. But those diagnostics will be strongly affected if the wind is very clumpy. And because it's easier if you have a clumped wind, it's easier for an electron and an ion to recombine with the same amount of mass, overall amount of mass. And so you have to correct for the clumping. But when people do that, I think that the general direction of this is to say that there doesn't seem to be enough mass loss to cause stars, the Kanti mechanism, to be very important. That when you see the transition from O and B stars to Wolf-Rayet stars, which have lost their hydrogen envelope, the Kanti mechanism is pretty hard to invoke for that because the mass loss is just not enough. And so I think the implication is then that the way Wolf-Rayet stars are produced is probably through some sort of binary stripping in most cases. Anyway, and then there's also an issue about metallicity. This Q bar parameter that I quoted is directly proportional to the metallicity of the star. And so for instance, when you compare the stars in the Magellanic Clouds, the small cloud is particularly where the metallicity is down by, I think it's nearly a factor of 10 or 20, at least 0.2 or so. Then you see that the winds are much weaker, and that confirmation of line-driven wind theory pretty much. But the distribution of alpha is hard to pin down directly from observations. It really comes out from theoretical calculations. Anyway, that's my best answer that I can give you right now.
Okay, let's move to the next question in the audience. Yeah.
Hello, Stan. Hi, Luca Fossati here. Great talk as usual.
Oh, Luca. Yeah, thank you.
I wanted to ask you if you can comment on the role of clumping in the winds of massive stars.
Yeah, I sort of just did. But the basic idea is that clumping can occur in many different ways. I actually have, let's see if I skip ahead here. There are some slides that I dropped. Let's see if that's too far. I have to go back to this, to the radiation driven. Well, basically there are two mechanisms for making clumps. More than two, but at least two. And let's see. Okay, I'm going to give up on trying to find this unless I scroll through my. Okay, so here's radiation-driven winds. And one of them is that there's this very powerful instability called the line deshadowing instability. Basically, if material is going a little bit faster than its neighbors, it gets an extra force because the Doppler shifts out of the absorption shadow. And that means it'll go faster still. And that leads to a very strong instability that I've spent a lot of my career studying. And this makes the wind extremely clumped. Clumping factors of order maybe up to, that is the ratio of density squared to density. The ratio of the average of density squared to density, which is normally the definition of clumping factor, can be 10 or so. And this again leads to overestimating if you just naively interpret the spectra, you overestimate the mass loss rate. But another source of clumping is that the winds can be initiated, especially from like Wolf-Rayet stars. They can be initiated by this iron bump. So this iron bump causes an initiation of the wind. In O stars, it basically just leads to convection and turbulence of the atmosphere. But in Wolf-Rayet stars, it can lead to a stagnated outflow. And then that stagnated outflow is sort of picked up by the deshadowing of line driving. This iron bump is basically a pseudo continuum of lots and lots of lines without taking into account the line deshadowing. And the net result is that then if you actually do multidimensional models, this is a paper by Nico Munz. So I think you'll actually give a talk, I think it's on Wednesday or Thursday, where he talks about in 3 dimensions, you actually get very turbulent winds just from the stagnation. But here the compression of the material is less. And so the clumping factor is less. But anyway, this is a lot of evidence that winds, both from O stars, OB stars, due to the line deshadowing instability, and from low-phase stars is probably very, very clumpy. And that's going to affect how one interprets diagnostics, because most of the diagnostics we have involve two bodies, the electrons recombining with ions. And there's a lot of work in modeling these. So, for example, ideally, you'd like to find a diagnostic that is not sensitive to density squared, but is singular density. And for example, the X-rays that come from shocks that are formed is potentially that type of diagnostic. But then there comes the issue about whether the medium is optically, whether these clumps are optically thin or thick. That's called porosity. And I've spent a fair amount of time talking about that. Anyway, I think there's been some work in using X-ray line profiles to constrain mass loss as a way of independent. And of course, there are other things. There are the electron scattering wings of emission lines. John Hillier's done a lot of work on that. But this is the key issue, is finding diagnostics that, most of the diagnostics that are easy to use, like H-alpha emission or radio emission, they're density squared diagnostics. But one is always seeking if there could be constraints that would be independent of clumping. Maybe X-rays are one of those, or these electron scattering wings of lines or another. That enough?
Thank you.
Thank you, Stan.
Yeah.
So I think we are ready at the time limit. I would like to thank you again for this beautiful talk. I hope you have a nice end of your Sunday. And hopefully you'll be able to join us virtually, remotely during the week. And
yeah, I'm a night owl, and so I should be able to stay up for at least the morning talks. They're in the Korean morning. Then the other ones I'll probably just try to listen to the recordings.
Yeah, perfect.
But I'm really sorry I can't be there, Aline. I wish I could. I just decided.
I know. I know.
But anyway,
we are happy that you were able to participate.
Yeah, I'm really very happy that you gave me this opportunity, because I learned a tremendous amount, and I think there's a lot of potential future discussions that we can have both in the conference and following up about how the physics of mass loss from stars is related to the that occurs from planetary.
Yeah, I'm looking forward for this week, and so I hope you to see remotely at some point. And I would like then to finish by a final round of applause to Stan, and I hope to see you this week.
Thank you very much, Aline. Good luck on the conference for the week. Bye-bye.
Bye-bye.